Dear students, back to the Visual Analytics lecture. Today I want to discuss with you clustering methods and also how clustering results can be visualized in order to assess their plausibility and whether they really help to bring up any relevant grouping in the data. Clustering can be applied to data of different dimensions. We will see some examples where the data is only two-dimensional, but also moderately high dimensional data with, let's say, 10 or 12 dimensions. In later lectures, we will see that there are methods that work also for even truly high dimensional data. Let's assume we have 50 dimensions where we have analyzed a lot of information about our customers, for example, and want to group them. That's quite interesting for business analytics. So there are other methods that are more local. Here we discuss first global clustering methods. You remember visual analytics is a combination of data mining techniques and visualization techniques, and the data mining technique that is important here is clustering. For those of you who have heard a data mining lecture, probably a lot of this is something that you are already familiar with. The outline of the presentation is as follows. I introduce and motivate the topic, of course, and then I present a number of clustering methods. First, a remark why there are so many clustering methods. One could think about people should compare them and then find out one clustering technique that is the best one, and that should be chosen in all circumstances. That's, however, not easily possible. Data sets are different and what we expect to see in the data is different. So there is a good reason that there are different clustering methods. They also are different with respect to their performance. So some of them would not work very well if we have really a large amount of data. That is this scalability issue that I have discussed already last week. So we start with the k-means algorithms. That's an easy one. It has some nice properties, but also a lot of disadvantages, and therefore other clustering techniques have been developed later, like optics and dbScan. Both are density-based techniques that assume that data that belongs to a cluster has a higher density. Density means there are more other elements, more other objects in the same neighborhood, in the neighborhood of a certain size. There are hierarchical clustering methods, bottom up or top down. We will discuss agglomerative hierarchical clustering. That means that as a result of the clustering, we do not only have one partition of the data from cluster 1 to cluster n, but we have a hierarchy. There is a partitioning at a high level where we may have 2 or 3 clusters only, and there are intermediate levels and low levels at the end where we have really a large amount of clusters. And then often the question is, for a particular application, should we choose one of these levels? The clustering algorithm provides clustering at different levels, and we may later decide about which level is appropriate for our particular application. And then we have clustering ensembles, which means that we cluster the data with either different methods, or that's even more typical with one method, but with different parameters. And as a result, we get different clusterings. And the question is, how much do they differ? How sensitive, for example, is the clustering result for changing one parameter a little bit? We will also discuss the clustering of categorical and mixed data. What does this mean? Typically, clustering methods assume that the data is scalar. That means that we have real values, like an income distribution, for example, or the age distribution of customers. But we also often have data that is categorical. For example, we are often interested in evaluating data with respect to men and female. That's not scalar data. So the question is, can we use clustering methods that process mixed data, where some dimensions are ordinal and others are categorical and others are scalar? Finally, a few remarks on multiple clusterings that should make you aware of the fact that there is typically not one true and correct clustering for your particular data, but there are different ways that could be plausible and valid, different perspectives to the data, one may say. Yeah. So for a reasoning process, it may be very useful to consider multiple clusterings. And the topic that I want to discuss in the end, very briefly, to be honest, but at least briefly, it should be discussed, I think, is temporal clustering, which means that we have time-dependent data, and instead of just clustering one time step, we are interested in developments over time. So clusters may merge over time, or they may split over time, they may grow or shrink. Yeah, these are typical situations that can be observed if temporal clustering algorithms are applied. So, and since this is a visual analytics lecture, I want to discuss this along with appropriate visualizations of the clustering results. So here's a very simple example to start with. Yeah, we see a small table of data. We have students. They only have a very short name consisting of one letter, and they have certain grades in physics and math. And we are interested in the fact whether there are students that perform similarly in physics and math, and this gives rise to this clustering. So we have two-dimensional data shown in a scatter plot, as we have discussed last week with several examples. And yeah, indeed, there are some students with rather low scores in both math and physics. So that was found as one cluster. Here is another cluster, almost elliptically shaped, with better results for both subjects. And here is one where the results are really good. By the way, you also see from this scatter plot that there is obviously a correlation. Yeah? Students that are very good in one subject are also good in the other one. Yeah? So clustering is part of an exploratory data analysis. That means users have very little a priori information. Yeah? This grouping process is carried out automatically, and therefore this is considered a type of unsupervised learning. Yeah, you know that in alternative there are also supervised learning methods where the a priori knowledge of an expert is represented and taken into account. So clustering means that we apply an algorithm to a large database, to all the elements there, and the members of one cluster are assumed to be closer to each other, so to say to the same group, than to the other clusters. Yeah? At least as an overall tendency. Perhaps a few elements of one cluster at the border of one cluster are closer to distant elements of the same cluster compared to border elements of another cluster. This still may happen, but as a tendency, members of one cluster should be closer to each other than to any other cluster. Clustering is based on a distance measure. Somehow we have to specify what we consider as distance. That could be quite simple. If we have scalar data, we could just say we apply the Euclidean distance. That can be done in any dimension. Yeah, it's not bound to 2D or 3D data. Works for any dimension. But it may be more complex than this. Yeah, if our dimensions have different ranges, for example, so one has only values between 0 and 1, and the other has values that go as far as 10,000, for example, then we need some weighting, some normalization in order to properly treat these different dimensions. Yeah? And in addition to the Euclidean matrix, there are also some other matrices that have certain applications where they are useful. So we have a distance measure, often the Euclidean one, but not always. Yeah. An example for normalization is here related to the car data set, yeah, where we have specifications of the horsepower, how powerful is this car, the number of cylinders that has another range, or for example, the maximum speed could be another element used to cluster cars with respect to, for example, being a sports car or more a family car. So that could be a result of clustering here. Clustering generally is thought to summarize homogeneous regions. Yeah, that means regions where the data are quite similar. Then there are discontinuities where we have large gaps in the data, and then there may be another cluster. In the beginning, when discussing the outline, I said that clustering may be also applied in a hierarchical manner. And often this is appropriate for the data, indeed. And that means a cluster may contain subclusters. That is, we have a region that has a relatively high density. That's why it's comprised as a cluster. But within this dense region, there are other small regions that have an even higher density, a subcluster within that cluster, whereas in other parts of the cluster, the density is relatively low compared to other elements in this cluster. Yeah, that leads to this hierarchical situation. I want to add a citation from Ling, this old paper from 1973, where already visualizations were used to assess the clustering results, as I have shown last week. He says that since data organization and presentation are among the objectives of cluster analysis, graphic tools to display the results of clustering are important. They should let one see whether the grouping of the data has brought out any latent structure. A latent structure is a hidden structure, information that was not obvious when just looking at a table with the data, for example. Yeah, so as motivation, clustering helps to understand the structure of the data, to define essential subgroups. I mentioned already the example of business analytics, where it is about customer segmentation and their behavior. What do they buy? What are they interested in? That allows targeted advertising, for example, for a certain target user group. And in the same way, in medicine, clustering is often applied in order to understand differences between patients, which of them are more likely to respond to a particular treatment, what are their properties. That could be a scenario where clustering is useful if it is applied to a database of patients. Yeah? Clustering is often a pre-process for a selective visualization. Yeah? That means when clustering is applied, I can present an overview with the data focused on a particular cluster. Yeah? The elements of that cluster are shown, for example, with an obvious color like yellow, yeah, saturated color, whereas other elements are shown as context only with gray values, for example, something that is not so striking for the eye. Or other elements may be even completely hidden. That's also possible. Yeah? So clustering is an essential information that may be used in the visualization of the data. Clustering may also be a pre-process for classification. Yeah? Often data is used to be classified with a decision tree, for example, and it could be useful to do this process separately for a few clusters. Yeah? So that is how clustering could be part of an overall workflow. That is a term we discussed last week, in particular in relation to guided visual analytics. So there are different steps carried out. Clustering is not everything. A visual analytics solution is not complete when only clustering and clustering visualizations are available, but it is an essential part of an overall solution. So we have two related tasks. One is to apply the clustering, that means to partition the data set. And the second is to display the clustering results with interaction facilities, and that is meant here with exploring the results, to interpret that partitioning and support reasoning. Now, these are the two tasks for clustering. Yeah, to go a little bit more into detail, clustering algorithms try to maximize the intercluster coherence. Yeah, that means the elements that are assigned to one cluster should be coherent, they should be similar, they should be close to each other. When we really see the data for the first time and have not experience with similar data sets, that means the distribution is really unknown to us, then we are advised well to apply different clustering methods, also to explore a bit the parameter space. That means adjust them and look at the results and look what we consider as plausible. Hopefully our system supports that we can store intermediate results for later reviewing them, reinvestigating them, and comparing them. Yeah? So if we have a better understanding, then we could have something in mind like a clustering model. We know, for example, that we expect as a result a certain number of clusters. Yeah? Sometimes that is really the case, that I know for this type of data I expect 3 clusters. I do not know exactly how large they are, what their shape are, where they are located, but I assume with my a priori knowledge 3 clusters. You see with this that although clustering in general is referred to as an unsupervised method, it's often helpful to know something about the data and to decide about the algorithm to be used and the parameters that could be useful as well. Yeah. So this cluster model could relate to the distribution of the data, also to the expected shapes of the data and their relations. What is meant with the shapes of the clusters? One particular classification that is useful here is whether we expect that the shape of our clusters is convex or it is non-convex. It may have arbitrary shapes, like a banana. Yeah? Something is convex if 2 points that are inside mean that the whole line that connects these points is also inside a cluster. Whereas non-convex means there are situations where we have 1 point and another point. Both are inside a cluster, but the straight line that connects them contains points that are outside of the cluster. Yeah? And some clustering algorithms cannot produce non-convex shapes at all. If I know this can happen, then these algorithms should not be used, for example. So a bit more in detail, what are different clustering methods and different clustering results? I already mentioned that you can apply clustering in a hierarchical manner. Then we have a tree with clustering results, and in a non-hierarchical manner where there is just one level where we partition the data set. That means we get a collection of clusters. We can number them from cluster 1 to cluster n. Clustering may be something that is carried out in a binary manner or in a fuzzy manner. Hard clustering, the typical clustering approaches is binary. That means an element is either assigned to one cluster, let's call it cluster I, or it is not assigned to cluster I. There is nothing in between. You cannot partially belong to a cluster or belong to a cluster with a certain probability. With fuzzy clustering, this is possible. Yeah? And that could be quite useful. For example, the elements that are in the center of a cluster are typically assigned with higher probability to that cluster compared to elements that are more in the border. Yeah, there it is a bit a borderline case. They could also be assigned to another cluster. So that means these elements would have different probability values for belonging to different clusters. The sum of the probabilities is 1, but there are more alternatives than being just 0 and 1. There are gray values in between. Some clustering methods are deterministic. That means when I start the clustering method, the result is always the same. Others are non-deterministic. That means for the same set of elements, they create different results. Yeah? There may be some randomness involved in the initialization, for example. Yeah? Often it is a good property of if an algorithm is deterministic. Sometimes it does not matter. So it's again something where you should keep in mind whether it's important to have deterministic behavior. So, and then, yeah, various distance measures can be used. That is a very important point for the yeah, developer of a clustering solution for the particular data that we have, what actually is important for measuring similarity and with this also distances. Clustering in general is a decomposition of the data um, and yeah, there may be also outliers. That is again something where the algorithms are different. Some algorithms force each and every element at the end to belong to one of the n clusters that are generated. Others allow that a point could not be assigned to any of the clusters and is then considered an outlier. Yeah, yeah, and a further result that some clustering algorithms generate, k-means for example, is not only the partitioning of the data in a number of clusters, but also one representative for a cluster. Typically, of course, an element that is quite close to the center of the cluster. That is then a representative. And that can be quite useful for some analytical tasks, but also for visualization. Yeah? Imagine that I have 10,000 elements and I get visual clutter when I want to present them simultaneously. But after I have clustered them, I only have 12 clusters. And instead of showing 10,000 elements, I show representative for the whole set of data, my 12 cluster representatives. That's of course much easier to interpret. Yeah, clustering may be applied to very low dimensional data. We have seen examples of two-dimensional data, for example, but also to data with higher dimensions. To make one remark that relates to later lectures, if the data is really high dimensional with more than, let's say, 20 dimensions, then it is very unlikely that you will find data sets that are similar across all dimensions. Yeah? Typically, elements are similar with respect to some dimensions and dissimilar with respect to others. And then a global clustering is not very useful because in this high dimensional space, basically the distance between any pair of points is quite large. Yeah? So there are so-called subspace clustering techniques that are more suitable if we have really high dimensional data. One use case of clustering that I will not discuss too much in the lecture, but I want to mention it at least because others would emphasize it probably much more, is clustering of documents. Yeah, a journalist may want to get a quick overview about a large set of documents that is related to a particular topic. And this clustering, yeah, of course, needs similarity matrix, and the similarity is typically defined by the co-occurrence of the same words. Yeah? If some words occur very frequently in one document and the same words occur again quite frequently in other documents, then probably they are similar and belong to one document cluster. Whereas if the frequently used words are different or even completely different, then they belong to another document cluster. Why this could be useful? As a journalist, I could be interested in getting a good overview. And then I would say, well, I should not read 12 documents that are very similar to each other, but it may be sufficient to read 2 or 3 of one cluster and then go ahead and read 2 or 3 of another cluster. Yeah? That means I get a better overview of the data, of the diversity of the documents and the text basically that have been written to a topic. Yeah? So document clustering is based on the frequency of words. And of course you need to pre-process this a little bit because otherwise some words like and or occur frequently basically in all documents. Yeah? If words occur frequently in all documents, they do not help to discriminate documents, they do not help for clustering, so they should be excluded. So I already mentioned that data has different types, and that is important for clustering. Often we have numerical values, termed as scalar values, but we may have also categorical data where we just have a small set of possible values, discrete possible values, like gender, male, female, diverse. Meanwhile, we have three types here, but not a large number. Yeah? And within our data set, we may have both simultaneously, scalar data and categorical data. Clustering, by the way, is also applied to image data, yeah, for those of you who are interested, for example, in medical imaging or industrial imaging, industrial CT, for example. There, clustering is sometimes used to find objects that belong together as a pre-processing step. In engineering applications, often streamlines describe yeah, the behavior of interesting structures. For example, in a virtual wind tunnel, streamlines describe the flow around a vehicle. And there are regions where the flow is quite similar and others where it is completely dissimilar. So therefore, streamline clustering could be useful for supporting flow visualization. Yeah, the streamlines that are assigned to one cluster typically are assigned one color, so that you can recognize the different clusters by clearly distinct colors. Yeah, that would be useful. A very special example, but I want to mention it because there is a number of researchers working on this. Fiber tract visualization in the brain. Yeah? In the brain, we have large fiber tracts that contain a lot of nerves important for the transmission of signals in the brain. And it is helpful that these fiber tracts are clustered in so-called fiber tracts, so that automatically they are grouped in the way that it is clear here are some nerves that go in the same direction and here are some that go in another direction. We will see a few examples of this. And I mentioned that we should also look in temporal clustering, and temporal clustering of course means that we have time-dependent data, and then it is not only interesting whether elements have the same value at different points in time, but also whether they have the same tendency. Yeah? So maybe there is a certain difference for the first point in time, but at later points in time there is the same difference. Yeah? That may be a reason to group them in a temporal clustering to the same cluster. Yeah. Clustering image data is similar to image segmentation. That may be a term that is familiar to some of you, at least those of you who have heard a lecture like medical image analysis. So here is this example of fiber tracts. Yeah? We have brain data and we have started an algorithm that searches for fibers in the data. And the result are all these many lines that you see here shown as streamlines. And they should be clustered. Yeah? By the way, this is the correct result. Yeah? Here is one type of clusters that belongs together here also, and this third one. How can I say this is the correct result? That's interesting. Typically, you don't have a ground truth in segmentation tasks and classification tasks. Here you have one. Namely, these are known anatomical structures. Yeah? For a neuroanatomist, it's quite clear what this bundle is about and this bundle is about, and that one also. Yeah? So here are different clustering results. This one has correctly separated this green part here, not completely correct, but largely correct from the red ones. But it failed to recognize this cluster at all. Here's another clustering results. This cluster is correct. This cluster is more or less correct. And then, and that is incorrect, this neuroanatomical structure here is subdivided into 6 different clusters, which makes no sense. Yeah? They belong together. So both are not right. The question is what is more disturbing, or what is more difficult to correct. Yeah? If I have this clustering result, an incomplete clustering result, then as a user I could have facilities to say I pick this cluster and this one and this and this and this and this, and trigger a command to summarize them so that they are then one cluster. Yeah? So I need to make a few clicks and then I can get the correct result. On the other hand, with this clustering results, I have a more severe problem. Yeah, I would have to manually select these individual lines here. If something is small, it's very difficult to select in order to tell the system, well, I consider this also one cluster. Yeah. So in general, an incomplete clustering is better than an incorrect clustering. Incorrect in the sense that things are summarized that do not belong together. Yeah, so I think I explained this sufficiently. Um, yeah, of course, the question is, what is a good distance measure here? Yeah, we want to cluster elements that are close to each other. Yeah, everything else makes no sense. But proximity alone could not be the reason. Yeah, probably this cluster here is quite close to some lines here, but the direction of the lines is completely different. So somehow the direction should be taken into consideration. And that's not so easy. What is the direction of such a fiber tract? Yeah, the fiber tract has many points. Which of them I should use to specify a direction? Maybe I take the first point and the last point and approximate basically the whole cluster by one straight line. That could be one option, not always the best one. Yeah, I could also look for the curvature of the lines. Yeah, I may have lines that are really quite straight, whereas others are strongly curved. That could be also a criterion to group or disgroup something. Yeah, here's a similar application that was carried out in our group where we dealt a lot with blood flow and blood flow clustering. So what you see here is a vascular structure in the brain, an arterial structure in the brain. And what you see here that should not be there, that is a pathology. Yeah, so there is a disease of this vascular system, namely a so-called aneurysm. Yeah, that grows here out of the parent artery. It may grow even further, it may rupture, and that would be a very bad situation for the patient. So therefore, there's a lot of research to understand what happens here in such an aneurysm. What about the blood flow? About the speed of the blood inside such an aneurysm, about the pressure with, which characterizes how strongly it hits the vessel wall here. Yeah? So that is the application background for this. Together with our colleagues from simulation, we generated yeah, a large number of streamlines that describe the flow inside this aneurysm. And the blood flow is clustered, yeah? And the distance measure here indeed includes proximity, direction, and curvature measures. Yeah? We carefully thought about this distance measure. That is actually the heart of the whole system, to come up with a good distance measure. And then we compute for every cluster one cluster representative. And this makes it possible that we show only, in this case, 8 cluster representatives instead of many, many other lines. And you see the advantage quite obviously. Here you cannot see anything that's inside. Anything that's inside is obscured. Yeah? It's not visible. It's completely occluded. Whereas if we only have a few cluster representatives, yeah, with this sparse representation, we can look inside. Yeah? So that is highly welcome by medical researchers to better understand the flow if we just can show a few representative lines. It's important, of course, that they are representative. That means that I do not miss any flow patterns like this spherical, vortical behavior that we see here, for example. Yeah? Yeah, so the choice of clustering methods, of course, strongly influences the results. We will talk about the k-means clustering algorithm that favors Voronoi cell-shaped clusters. We will look at density-based clusters. And yeah, as a remark, we worked together a lot with the data mining group here at our university. Even these experts try different algorithms and different parameters. It's not clear from the beginning for this type of data, we should just take this algorithm and these parameters, and that gives the best result. Yeah? We will later talk about how to assess the quality of clustering. That is not only a matter of taste. I like this clustering more than this one. but there are measures for cluster quality, for cluster coherence, for example, that support the quality assessment of clustering results. Yeah, so back again to this overview, these are the methods that I want to discuss in the following. Before doing so, I want to classify the clustering problems a bit so that we see what is so different about clustering problems and why we need different algorithms to cope with them. There's one paper from Michael Sedelbayer and colleagues where this image is from that is really a seminal paper on clustering and its use in visual analytics. It tries, for my taste, in a very good manner to characterize the different situations that can arise if we have high-dimensional data. That's a lot of sun here. So I'm back and there's not so much sun. So we have situations where we have few points to cluster or we have many points to cluster. And that is an important discrimination because some algorithms tend to be quite slow if we have many data points. They are not scalable so well. Therefore, this is an important difference. We may have clusters that are quite small, or we may expect large clusters. We may have a data set where basically all elements are far away from each other, which particularly happens if we have more high-dimensional data, or we may expect denser data. That means objects in general are quite close to each other, even those that will not end up in the same cluster. Clumpiness is another parameter. Yeah? We may have at the one extreme data that is equidistant. Yeah? So basically, if you look for one element of the data set, how far away are your three nearest neighbors? Then the result is basically the same for all elements. The nearest neighbors are all in a certain distance. If this is the case, by the way, I would say clustering makes no sense. Yeah? Clustering has the assumption that there are denser regions and not so dense regions, and that means indeed there are data sets where clustering just does not produce any meaningful result. Yeah? Here we have many dense spots. That's a different situation. Here we have one dense spot. Also a difficult situation for clustering. So probably clustering would result here in one cluster representing the dense spot and everything else is considered an outlier. At least if a density-based clustering is applied. Yeah? So outlier is another parameter that is different for the data sets. We may have the situation that we have no outliers at all, which would be great for clustering. We may have a few outliers, or we may have relatively a larger number of outliers. Many here may be 1% of the data. Yeah? Let's assume we have 10,000 data and 100 of them are outliers. And some algorithms, clustering algorithms, can consider outliers and handle them, whereas others do not consider them at all. They basically assume there are no outliers. Yeah? So then we briefly discussed already the shape of clustering results, and you see here the isotropy. Isotropy means something is isotrope if I can look at it from different directions and it looks the same. Yeah? That's true for a circle. So we may have narrow structures or curvy structures, and here you see that we have cluster shapes that are non-convex, whereas these three here are convex. Yeah, and there are even more things that need to be considered and that make clustering problems different, namely the relations between different clusters. Yeah? We may have the situation that our clusters probably have the same number of elements as shown here, but there could also be good reasons to have clusters with rather few elements and much more elements for another cluster. We may have situations where the clusters differ in size quite a lot or not so much, or in density. Some algorithms, density-based algorithms, cannot handle the situation very well that the density over the whole data set is quite different, because that would mean that what I consider a dense structure is different depending in which region of the data I'm looking. Yeah. So elements may be interwoven or they may be equidistant or randomly distributed. So here we have a situation that's also tricky. There may be good reasons where we do not require that the points belonging to a cluster are spatially very close. They may have the same behavior, yeah, customers that are very similar, but they live in quite different regions of the country, for example. Yeah, so that leads to a split clustering situation. Yeah, this is a set of of orange points, and this is also a set of orange points, and this should indicate that all the orange points belong to the same cluster. Also, this is not one connected component. Yeah, sometimes this happens, and then you need a clustering algorithm that can handle this. Yeah, the shape can be different, of course. Yeah, position inside and outside may be different, and we may even have situations where clusters are fully separated or even distant, but also situations where they may overlap. Yeah, um, overlapping clustering is a situation that you can only handle with fuzzy clustering. Yeah, because with fuzzy clustering, you can specify or you can get as a result that an element belongs with a certain probability to different clusters. Yeah. So here are the different between class features shown. That's from the same paper from Michael Sedelmeier and colleagues in the Journal of Transactions on Visualization and Graphics. So I indicated this already, but let me summarize it once more here. The results of clustering may be hard clustering, which means that each object is assigned to one cluster, to exactly one cluster, not to 0 clusters, but never to more than one cluster. The exception is that some elements may be considered outliers. That is possible with some approaches. So then an object may be assigned to 0 clusters. Fuzzy clustering gives membership degrees as a result, and for clusters we may compute a representative that may be close to the center of the cluster, um, but again care may be necessary in case that we have non-convex clusters. Then the center of the cluster may be outside of the cluster, which is strange. But if you think about a non-convex shape, it may easily happen. Yeah. So what we also can do in order to visualize a clustering result is, instead of showing all the individual elements within a cluster, maybe all the individual nerve fibers or blood flow streamlines or whatever, we can generate a hull surface, a comprising surface, so that all elements of that cluster are inside. Yeah? So that is something that also may be done. We talked about regression lines last week as an important analytical result when we are interested in looking for correlations in data. If we think about this again, once we have applied a clustering algorithm, it may be a good idea to compute a regression line for each and every cluster. Yeah? And it would not be too surprising if these regression lines are quite different. Yeah? That means just that the kind of correlation for different subgroups of the data is different. Yeah, I briefly want to discuss requirements. I think that's always a good idea before you think about some methods to solve a problem, that you think about what would your ideal solution would be. So here I would say an ideal clustering method would be applicable to many, many objects. Let's say some millions of objects, and also to many dimensions. Let's say a few hundred dimensions. Yeah. It may create clusters of arbitrary shapes. That means it is not restricted to particular shapes, ellipsoids, for example. Data is never perfect. That's something we discussed last week when we briefly thought about data cleansing. Data may be noisy, data may contain really false values, and some outliers typically represent false values. For example, when a sensor is no longer working properly. So ideally, a clustering method is robust against noise and outliers. And it should create plausible results even in a situation that is difficult for most clustering algorithms, namely that the density in the data is not the same, the average density. Yeah. So clustering may be based on some model assumptions. A distance model is one possible assumptions that we can use when thinking about a clustering method. That means objects should be assigned to a cluster if they are closer to their cluster center. Yeah, we have the index I here for the cluster and for the cluster center than to any other cluster center. Yeah, this is the kind of model assumption underlying k-means clustering and variance of k-means. A density model, on the other hand, um, makes the assumptions that objects should belong to a cluster if the density in their surrounding is high compared to the average density. Yeah? I already briefly mentioned how density can be computed. So for example, we could ask what are the distances to your 3 or 5 nearest neighbors, and then you get typically quite different results for different elements of your data set. And whenever you have a high density, then you should look for a cluster in the surrounding. dbScan is, yeah, I think the most popular, the conventional density-based methods. Optics is a method that in most cases performs a bit better. We will see examples where this can be actually seen and evaluated. Yeah. So, and sometimes I may assume that I have a hierarchy of clusters, and then of course I should use a hierarchical clustering method. Yeah, so k-means is a clustering algorithm that partitions the data set in k groups. K is an important parameter that has to be specified in advance. That means I have to know before applying clustering how many clusters I do expect. And I get exactly this number. Yeah, if I say I want to have 5 clusters, then k-means gives me 5 clusters. If for this particular data set 5 clusters is not very meaningful, the algorithm, yeah, has no way to produce any different result. Yeah. So the clusters are defined in such a way that the sum of the squared distances from cluster elements to cluster centroids is minimal. Yeah. So with this, it's clear that k-means clustering is a kind of optimization problem and variance minimization. In the requirements, we briefly discussed that ideally an algorithm should be robust against outliers. Yeah? K-means is not robust against outliers, and that becomes immediately obvious if we look at this expression here. We minimize quadratic distances. That means if we have an outlier, an element that is far away from other elements, that strongly pulls the whole cluster in this direction because this large distance is even squared. Yeah? And k-means does not recognize outliers. It assigns each and every element to a cluster, even those that other algorithms would consider as an outlier. Yeah? So with this, I start already to discuss some properties. K-means works as follows. It starts with an initialization that is typically a random process, so it's not a deterministic algorithm. You could also make it deterministic by saying, well, I take the first k elements, let's assume k is 5, then we say, well, I take the first element, the second until the 5, the fifth. These are my 5 initial cluster centers. And I assign all elements to 5 clusters depending how close they are to these 5 elements. And then probably it turns out that this is not a good idea with respect to this formula here. And I change this, I use other initializations and finally come up with a good result. This optimization process is one that leads at the end to a local optimum, not to the global optimum, because the global optimum is too hard to compute, that takes just too much time. Yeah, that is what I mean here. The problem is NP hard. That means that there is no algorithm that can compute the global optimum in a complexity that is a polynomial of the number of elements in the data set. Yeah? And we typically have to consider large data sets with several thousands of points, and then an exponential complexity is simply not scalable. So therefore, in practice, numerical algorithms approximate the solution here, and that is typically a local optimum. So here we see a result. Actually, we see two results from two clustering algorithms, k-means, which I have explained, and expectation maximization, which I have not explained, but want to mention it at least because it's a typical algorithm. And you see that k-means has the tendency to produce clusters of the same size. Yeah? If you would count how many elements here are red and how many are blue and green, that would give roughly the same number. And that is not an adequate clustering for this particular data set, as you see. Yeah? Here that is much, much better. You see here we really have a coherent structure. Here we have a coherent structure. And this one has a lower density, but still it belongs together. By the way, if you look carefully, you also see the cluster center. Yeah? So here is the cluster center, that's the cross. Here is a green circle, that is the cluster representative. And here is something in this red part. Yeah? So these are two clustering results, and I think it's fair to say that in this example, expectation maximization is the better algorithm. So, by the way, an interesting property of k-means is if you would include in this visualization, in this scatter plot, the boundary that can be constructed that connects all the boundary points here of a cluster, then, and you do this also for the other clusters, that leads to a Voronoi decomposition of the space. Yeah, so some properties of this algorithm. Euclidean distance metric works only for numerical data. The clusters that result are always convex, and the algorithm is not robust against outliers. Yeah? And another problem is, of course, the very property of this algorithm, namely to generate k clusters, means that you must know your data quite well, in the sense that you expect exactly a certain number of clusters. We discussed in the beginning that clustering is an unsupervised learning method where you don't need a priori knowledge. It is for exploratory data analysis. Well, obviously with k-means that is a trade-off. You need to know something about the data. For example, that convex clusters are typically appropriate, and that you expect a certain number of clusters. Yeah, so what happens if k is too small? If k is too small, then you group elements that you should not group. If you think back to this example of the fiber tracts, that was the situation when we had a too small number of clusters, and that is more difficult to correct. Yeah, I termed this there as an incorrect result. If k is too high, the clustering is incomplete. Yeah, we could summarize some clusters, but that is easier to correct. So if I would be in doubt about what is the number k, I would better choose a k that is slightly too high than slightly too small. So, and another property, we have seen it in the example already, is the clusters have a similar size. Yeah, and the result depends on the initialization. K-means clustering is widely available in many libraries, so if you want to make some own experiments with K-means clustering, it's not necessary that you develop this algorithm yourself and implement it yourself. You can just use it from VK or OpenCV, for example. Yeah, some improvements related to K-means clustering. You can improve the performance with hierarchical data structures such as a KD tree. Yeah, that gives better starting points, a better initialization. A KD tree is one where you first make a distinction along one dimension, which are the elements that have higher values and lower values. And then you do this again for a second dimension, for further dimensions. So that gives you a hierarchical structure, which is then quite useful to select the points for the initialization from. So there are also other attempts to improve the convergence of this optimization algorithm. I said that one drawback is that you have to know the number k in advance. For the basic algorithm, that is definitely true, but there are extensions that allow you, instead of specifying a specific value for k, to specify a range. So for example, apply the algorithm with k from 5 to 20. And then the algorithm is indeed carried out for all the intermediate values. Yeah, so it generates actually 16 clusterings. And based on some quality measures, it tries to find one k value that is optimal. Yeah, that could support the analyst, of course. Yeah. So, and then of course there is fuzzy C-means, which is the extension of k-means to fuzzy clustering, which actually means that you don't have a hard clustering, but instead fuzzy memberships. The probability that an element belongs to a cluster, of course, is maximum and typically 1 for the cluster center, and it's much lower and yeah, at the borders of a cluster. So it may have the same value for two different clusters. Yeah. So other properties are quite similar to k-means, for example, the overall shape of the resulting clusters. Let me briefly comment on this estimating the number of clusters, yeah, that we get rid of this assumption we know in advance how many clusters we will get. So that is based on a certain matrix. Yeah? X-means is one of these examples, and the X-means algorithm, I cited the paper where this was introduced, is realized in R. So if you use in the exercise R, then you may use also a k-means variant that estimates what is the best value for k. So, and let me show at least briefly, formally, what does it mean to apply fuzzy clustering, fuzzy C-means clustering. With this, we assign a membership degree to all of our elements in the data set, and the index I stands here for the elements of the data set, and the index k stands for the clusters. Yeah? So mu yk is the probability that the element I belongs to the cluster k. And such a value is produced for all i's and for all clusters k. Yeah, and the values are in the range between 0 and 1. Yeah, it can never exceed 1, but it can also not be negative. Yeah, and the sum of all the probabilities for one particular element I is 1. Yeah, so if I have a rather high degree of membership to cluster 1, for example, then the overall probability that the element I does not belong to cluster K is quite small. Yeah, if we have already 0.8 for cluster 1, then the sum of all the other probabilities can only be 0.2. Yeah, so and of course, if we sum this up for all the n elements, that is between 0 and n. Yeah, you see, approximately the same formula that we have already seen for k-means clustering, but now we have these fuzzy membership degrees here, these values between 0 and 1. Yeah, that is part of this functional, and we again optimize in the sense that we want to reduce the squared distance of elements to their cluster center. That is a non-linear optimization problems, and yeah, there are different algorithms that can be used to solve this. Genetic algorithms have been applied to this, or also simulated annealing. I don't want to go in the details here with the algorithms, that would be part of a data mining lecture. I just want to give you a little impression of what happens under the surface of an algorithm here, so that you have at least little information to assess the results. Yeah. Yeah, so we have density-based clustering, where clusters are characterized by an above average local density. And yeah, that is the topic that we will discuss next week. Yeah, I want to summarize so far. We've discussed several clustering methods and their properties. So far with a focus on k-means clustering and fuzzy c-means clustering, that have certain restrictions and are the reasons why there are other, one could say more modern algorithms that are used for other clustering problems. Yeah, with this I want to thank you for your attention.